Good morning, everybody. I do apologize for yesterday not getting you your lab packets. I'm sure you were very disappointed that, we had to go through all that together. It was actually one of the more successful circuits labs I think I've ever experienced, so I blame you guys for that, not me. I touch a circuit and it goes bad right away. But let's see, we're in our final day of lecture for this unit, because on Monday what's happening? Review, right? And then we take the exam on Tuesday. Golly, wow. Everything happens so fast. How has this unit been? I mean, how are you feeling about the material? Better than the last one? But you're still not quite sure on a lot of this stuff, I'm assuming, right? There's always that fear and trepidation that you just don't know. And you don't know. You're new to this. It's okay to not know, right? You need to not know at a certain level, I guess is what I'm trying to say. But was I correct? When I said that the second unit's going to be easier than the first, is that sort of the general impression? You'll probably let me know on the exam, after the exam, how you feel. Just don't key my car, slash my tires or something. But yeah, in general, the math isn't real hard here. It's just a lot of keeping track of stuff, isn't it? So yeah. Don't forget about electric potential. That was that sort of carryover chapter that did have some integration and things in it. So don't forget about that. Try to review that over the next couple days as you start putting your cheat sheet together and things like that. But let's finish up this Kirchhoff's rules example, and then I want to talk a little bit about how houses are wired and something called an RC circuit, and then maybe we'll have some time to go over homework. So we got to this point last lecture, and I sort of left you hanging a little bit on the solution here, but I said that you've actually done this before. Did anybody remember where they'd done it before? It's lab number 1, problem number 1. I'm not sure I gave you exactly the same numbers, but I think they're pretty close. Those 3 equations in purple might have been the equations that I gave you. And then I said, solve 3 equations for 3 unknowns. So in general, you've done this or something very, very similar to it. Solving systems of equations can kind of go bad fast. You can end up sometimes in these loops, these endless loops where you can never quite get it. But the goal here, right, is to get one equation that just has I1 in it, or just I2 or just I3. And these 3 equations should be able to do it. Now, this can take a while if you do it with raw algebra. It's doable, but it's a headache. So I want to show you how to do your homework quickly. Okay? Realizing that most of you probably haven't seen this method before. It's a method that comes out of linear algebra, which is it math 17? Is that math 17? And a lot of you haven't had math 17 yet, which is just fine, okay? But rather than do this the brute force algebra way, there's a slightly different way that we can do this. And the way we're going to start this is we're going to clean these up. I'm going to use a bigger, there we go. We're going to clean these up. And by clean it up, I mean I'm going to try to get the variables on one side and the constants on the other, I think is what I kind of want to do here, right? So let's see. I can clean this one up by writing this as 41 let's make it cleaner. 30I1 plus 41I3 equals negative 45. What did I just do to that equation? I took this and moved it where? Bonk, I put it on the other side, right? What did I do with this one? Same thing, right? and then for some reason did a negative 45, which is not right, which is why you always go back and check. Okay, what I did there is I managed to put anything that had a variable in it on the right-hand side, and then anything that was just a constant on the left-hand side. Let's do the same thing with the second one here. This would be 30I1 minus 21I2 equals negative 80. Did I did that one right? Yep. Okay. Again, move the 30I1 over, which flips its sign. Move the 21I2 over, which flips its sign. Flip signs right there. And then the negative 80 stayed on that side of the equal sign, so negative 80. Okay. And then I do the same thing for the last equation. That one's going to be kind of interesting, right? So this is going to be, I'm going to do I1 plus I2 minus I3 equals 0. What did I do there? I3 went to the other side. When it goes to the other side, what happens to its sign? Flips, right? Okay. And then that leaves 0 over here, and then I just reversed the order of where the 0 was. Okay. So I've kind of got these equations arranged in a specific pattern, so to speak, where I've got 3 unknowns, don't I? So I1, I2, and I3 are all my unknowns. I've moved anything that's got an unknown term in it to one side, and then anything that doesn't have any unknowns, in other words, all the constants, all the known values, I've moved to the other side. And the reason I've done that is I'm setting this up in a way. This is referred to as a linear system of equations. Basically, a linear system of equations is any system. You can have n unknowns, and to be able to solve for all of those unknowns, how many equations do you need to have? Minimum? N. In other words, if you've got 5 unknowns, you need 5 equations minimum to be able to solve for all those unknowns. If you have 10 unknowns, so on and so forth, you just need 10 equations. So what I've got here is I've got 3 equations with 3 unknowns. Something that computers are really good at is solving things like this, right? And so I'm going to do that. Let's see if I can flip back and forth quickly. By using this thing called a linear solver. You can literally go to Google, okay? I haven't checked to see if ChatGPT can understand linear systems of equations. I bet you it can, but I just type linear solver into Google, and ever since the internet was invented, the very first link has always been the right one for linear solvers. I don't know what it is, but this linear solver is great, okay? And so you get to this page, and you've got different methods that you can put things in, okay? Either the integral, matrix, or individual method. Choose individual, okay? And it pops up with this box of stuff here, right? Okay? So notice there is a pattern. What they want us to do is put in coefficients, okay, for the system of equations that I have. So if I go back to my problem here, right, I've got this system of equations. Let's just put it on the board so that I don't have to keep flipping back and forth. So I've got 30I1. Notice I've got a box with x plus a box with y plus a box with z equals something. That's the pattern I'm going for here. So I have 30I1. What is my I2 for this top equation? It's 0I2 plus 41I3 equals 45, right? And then if I rewrote the 30I1 plus or minus 21I2 plus 0I3 equals negative 80. And then I just have I1 plus I2 plus minus I3 equals 0. What are the numbers in front of I1 and I2? 1. And what's the number in front of I3? Negative 1. So there's the pattern, right, that a linear system of equations this website actually is wanting us to do, okay? So I come in here and I type in these coefficients. It would be 30, 0, 41, and then what do I put on the other side of the equal sign? 45. And then for the second one, it's going to be 30, negative 21, 0, and negative 80. And then 1, 1, negative 1, and what do I put in? 0. Okay? And so that should, yeah, there it goes. Okay? So it shows me that did it interpret my system correctly? 30x, which is my I1, plus nothing I2, plus 41z, right? The third variable. So on and so forth. Okay? So it looked like it interpreted it correctly, and then it punched out these numbers. It's a math site, so they're always going to leave it as fractions. Okay? But I got, so I think that first number right there, the negative 2335 divided by 2721, I got that as, oops, I1 was negative 0.858 amps. I2 was 2.58 amps. And I3 was 1.73 amps. I'm just going to say bilinear solver to remember what's going on. Okay, so why did I show all that to you, right? I think it's faster to get it into a format like this and then let a computer do it than it is to have to sort of hand do it via algebra.
Can we do this with the calculator?
Yeah.
So calculators can do this. Okay, there are linear solvers on calculators. Your phones can do this with certain apps. But now so I'm showing you this and I'm telling you, do it this way on your homework. Don't waste time on algebra on your homework. Focus on setting up the problems correctly, right? And then get a computer to solve your equations for you. If you had a circuit if you had equations that had 4 currents in it, right? And 4 equations, you go to that website and then you would have to change, like you need 4 equations with 4 unknowns, right? And then it would change it so that you would have more boxes, right? To be able to do the system with. So you can use this linear solver. Just Google linear solver. It's always the first one that pops up, okay? Even doesn't matter what your cookies are or anything. For some reason, it's always the one that's at the top for everybody. So linear solver. Wolfram Alpha can do it. It's just the syntax is a little bit harder in Wolfram Alpha, but it can do it. Calculators can do it. What do we do about the exam? Okay, calculators. But not everybody in here has a calculator, has a linear solver on it, right? So this is where I get tricky. And not tricky in the sense of trying to fool you, but tricky in the sense of how do I test what you know without having you do busy work? And so Nico said, just do the setup. Now you'll notice I posted the topics for you guys, right, for your exam?
Yeah.
I'm questioning everything now that I forgot your lab packets. Did I do this? Yes, I did. I think it says Kirchhoff's rules times 3.
Yes.
Was that right? Okay. So what I've done, and I kind of mentioned this earlier about the other circuits problems, is I've kind of taken parts of Kirchhoff's problems and broken them up. So like you can expect a question where here's the circuit diagram. What's the equation for this loop, right? And I've shown you, I've like drawn the current, whatever, right? Okay. So that's testing what? What am I trying to find out if I give you a circuit diagram and ask you to write the equation down for the loop? I'm trying to test if you know Kirchhoff's rule, loop rule, right? And I could say the same thing for a junction, right? Okay. But then I could ask you a question that has you having to do all the loops. Let's say I give you a question that's a little bit like this one right here, okay? And I'm like, okay, I'm expecting you to be able to set this all up. how could I make this faster to do mathematically? Give you one of the currents, right? If I give you one of these currents, all of a sudden it's two equations with two unknowns, and I expect you to be able to do that on a test. Okay? I can give you two of these currents, and then it would be just stupid easy to find the other one, right? But I can still ask you for the setup. So I am not going to ask you to do more than two equations for two unknowns on the exam. Okay? We just don't have time for you to waste working through linear algebra. I don't want to set up it's not fair somebody has access to a linear solver and somebody else, because now I've got to police calculators and do all that baloney, right? I'm going to test whether or not you can set up circuit problems, right? And then if there is some element where I'm asking you to solve for a current or whatever, it's going to be at most two equations with two unknowns, which you should be able to do just by direct substitution, right? Solve for one variable, plug it into the other, done. Okay? So that's kind of how I've worked out over the years to test students on Kirchhoff's laws, circuit things, without having you spend a lot of time in the algebra part, the math part of it, which I'm less interested in. What happens to you if you set up the problem right but get the math wrong? You still get it right? What is the exam autopsy for? One thing that it's for? It's for you to come up and say, Mr. Balogh, I set this up correctly. I got the math wrong. Can you give me credit for this? What am I going to say? Yes. Right? For those many of you that came up to me during the last one and said, Mr. Balogh, I think I set this up right. I just did the math wrong. I was like, great. You set it up right. Good job. I can't catch everything, right? So the test autopsy is your opportunity. But so get it down on the page during the exam. Get something down, right? Because I will always grade off of what's on that page. And some of you were like, but Mr. Balogh, I knew it. It was in my head. I was like, I can't see into your head. I don't want to see into your head, right? Show me what you know. Communicate to me what you've got, right? And then we'll take it from there. So I guess what I'm trying to say to you is, while you're doing your homework, you are going to run into like 3 equations with 3 unknowns or something on your homework, okay? Let the computer solve it, okay? Just do it. You're not losing anything by doing that, right? Get the computers to solve it and move on and focus on the concepts. All right, let's see here. You're in the 11 a.m., aren't you?
Yep.
Okay, I'll give that to you. Start this one on this side. I think these are your drawing of the electric field labs. I think those are what's in there. Okay. Questions, comments, or concerns about what I'm expecting?
On the exam, are you gonna draw like the current lines, like where they're running, or are we expected to draw?
Did everybody hear the question? No? Okay. So Apple's asking, on the exam, are you going to give us the current direction, say on a circuit diagram, or are we going to have to choose? The answer is yes. For some problems, I'll specify it because I want to basically have the same answer so it's easier for me to grade, right? But on other problems, I could leave you to your own devices and still see if you've got the answers or not. So yeah, both. Some I have given you the current direction, others I'm leaving it up to you. So let's back up and talk about this negative sign right here. Do you see how we got 2 of these currents positive and 1 of them negative? What does that mean? A negative current. It meant that the direction I chose was incorrect at the beginning, right? It means that I1, instead of flowing upwards out of point A and going around, is really flowing into point A, isn't it? Okay? So that's what that negative sign right there means. It just means that I got the direction backwards. What is the current in that branch? It's 8.58, right? 0.858. That's what the current is. The direction sometimes matters, but usually doesn't, right? I can solve for the currents. Now that I know the currents, I can get the powers through those resistors, the voltages through those resistors. I can use Ohm's law to do that, all that sort of stuff. What kind of circuit would have two potential sources in it across a load where those batteries are like kind of connected to each other like this? Can you think of any situation where you would have two batteries in a circuit? What is this brick doing to the battery in this computer? It's charging it, right? This is basically a recharging circuit. To charge a battery, don't you have to put a potential across it? This brick's job is to take the AC and turn it into DC. So it's effectively a battery, a source of potential of its own, and that's going to the laptop battery. So I got two batteries in this circuit system, don't I? A source of potential here and a source of potential in the laptop. If they're working together, right, then current flows one way. But if I need to recharge the battery, I've got to reverse current through it or something like that. It's more technical than that. But it's very easy to come up with multiple sources of potential in a circuit. Another way that we can come up with a source of potential in a circuit is to throw a capacitor into these circuits. Remember capacitors? What do capacitors do? They store energy, don't they? Store energy in the electric field and then give that energy up, acting as a potential source. So, how do we deal with that? Before we get to capacitors, let's just talk about your house. Just so you know, right, what's going on here. Okay? They always look surprised to me. Even before emojis were a thing, outlets always look surprised to me. Does anybody have outlets in their house that are upside down? You run into that? Okay. There is no standard for what the orientation of the socket is. Anything you've heard about whether like a socket is upside down or right side up, meaning it's grounded, not grounded, switched, not switched, any of that kind of stuff, it's baloney. Okay. There's no standard in the electrical code for orientation of sockets, so you can put them any way you want. Sometimes electricians will put one upside down to indicate that it's different, say, from its neighbors, right? It could be wired differently. Does anybody have like outlets in your house where they are connected to a light switch, right? And you can turn lamps on and off, right? That kind of thing. So sometimes I've seen electricians invert those to indicate that it's a switched outlet as opposed to an outlet that always has power. But again, there's no standard, and generally, I always do it with the surprised open mouth down. What is this hole? That's the ground, okay? That wire is connected literally to the ground outside of your house. It's connected to the circuit box on the side of your house, and then that circuit box has a grounding wire that is either attached to a metal stake that's driven into the ground, or more often than not, like the gas line that's coming into your house, okay? Because the gas line is a metal pipe that comes through the ground. But either way, there's a direct connection to the literal earth outside of your house, and that's what that bottom thing is. Then we've got the one that's like a regular eye, and then we've got the eye that's a little bit longer, okay? So I don't know if it's crying or has Bell's palsy or something. I don't know what's going on there, okay? So which is which? Like, what's going on? You know the voltage that comes out of a regular household outlet. What is it? 120. So that number is actually the high range. There's a low range as required by law. Anybody know what the low is? 110. 110 to 120, with the average being 115, which is why sometimes you'll see things say 115 volts required. It can run at 120. It's just fine. It's just saying the average. Okay? 120 is typically like what everybody talks about because Europe is running on 240. But again, they're running from 220 to 240. But there are connections. This is really hard to see because I use like the worst colors you could possibly use on a slide. I need to fix this. Okay? So we got the ground. Oh, I used the colors of the wires. That's what I tried to do. Okay? Neutral and then hot. Okay? So neutral wire is typically a white wire, although, again, it's not in the code that it has to be any color, but generally it's a white wire that connects up. And it is the reference line. PG&E tries to keep this as close to ground as possible because you're wasting energy if it's not. But it's not the ground. It's simply a reference for the hot wire. And PG&E has to maintain 115 volts on average between the hot and the neutral line. Both of those lines come into the house from the power cables outside. So that means that if the neutral is at 100 volts with respect to the ground, what does the hot have to be with respect to the ground? 220, right? What's the difference between 100 and 220? It's 120, right? But like I said, PG&E does try to keep the neutral as close to ground. And what's ground in terms of potential? It's 0, okay? So it tries to keep the neutral as close to, but there's things that change that fluctuate all the time in the system. And so, but it's usually like within 5 volts. Right? It's really, really close. Okay? But they have to be, it's more important that the neutral wire and the hot wire be hooked up correctly on the back of the outlet. Anybody that's ever pulled these out of the outlet box knows that there's a lot of ways that this can go wrong. Okay? A lot of ways. There are, I think, there are 9 different connections on the back of a standard outlet. Okay? That's 9 places you can put a wire. You've got 3 wires. You've got 9 places to put them. And this can go wrong in a hurry. Right? Electricians, licensed electricians have to be very careful that they don't swap wires around as they're hooking stuff up. One of the more dangerous swaps is to swap ground for the hot wire. Because when you plug a device in, it's expecting which prong is going to be which, right? And if your ground is the hot wire and you're sending electricity through the ground to your device, that thing can blow up in a hurry. So if you're never sure about how to hook these things up, don't trust YouTube. I've seen some bad advice on YouTube about hooking these things up. Okay? Find an electrician or somebody that knows what they're doing and do it right. Okay. And there's also ways to test that, by the way. You can buy these little testers. You just plug them in and the lights tell you if it's hooked up right or not. When I bought my house 2 decades ago, I bought a tester and I found 2 outlets that weren't hooked up right. They were, the swap that is the most common swap that's wrong is hot and neutral being swapped, which isn't as dangerous as a ground swap. All the grounds were good. So this is a schematic diagram kind of how your house is kind of hooked up. You've got the neutral and live lines coming in from PG&E. They go through the meter, okay? And the meter's job, of course, is to find out how much money you owe. But after the meter is the circuit breaker box. And inside of that box, you have different circuits within your house. Those circuit breakers are designed to trip when the current gets too high in the wire. We don't want high currents in wire because we don't want them to heat up too much. So a standard household current is 15 amps. The wire can do like 30 amps before it starts to get hot to the point where it starts to burn, right? But we make sure to not exceed, right, a certain level by code. If you need a circuit in your house for like an electric stove, electric water heater, electric dryer, something that's running on a higher current and usually a higher voltage, 240 volts, at say 60 amps or 30 amps, they'll use different sized wires for that. It's called wire gauge, and the wires get thicker to allow for more current to flow and not heat up as much. They're trying to keep the house from burning down. That's the goal of a circuit breaker. Not necessarily designed to keep humans safe. As we know, 15 amps is well in excess of what it takes to kill you, right? But we're trying to keep the heating in the wire to a limit. And part of the reasons that there are building codes is to make sure that there isn't a single wire in your house that is too long. What happens to the resistance as you increase the length of a wire? It gets bigger, doesn't it? And the more resistance, the more current, the more heating there is, right? So there's limits to how long a wire can be, a run can be in your house before it must be terminated, amplified, switched, or something, right? So as again, to make sure it's not going to heat up too much. But those circuit breakers are hooked up how? Series or parallel with the rest of your house? They're in series, right? We want, when that circuit breaker cuts, we want to be able to turn the power off. Which is why sometimes if you've had the lights go out in your house, right? All the lights are gone, say, in the bedrooms, but the lights are still working in the kitchen. Your bedrooms are all on a different circuit, right, than the kitchen was. And whatever happened to that circuit caused it to trip, happened. I don't have a picture of it, but I'm guessing many of you now have an outlet in your house that's got two little buttons in the middle that say test and reset. And it's probably like in a bathroom or a kitchen or maybe the garage, okay? That's called a GCFI, ground control fault interrupter. It's basically, what it does is it monitors ground to make sure that that circuit is always connected to ground. That's really important around sources of water because the water can become an electrical connection between the ground and the circuit that doesn't pass safely through the ground connection. In other words, it could be passing through you, okay? So for two outlet device, so for two-pronged devices like this drill that this guy is holding, if you reverse, okay, the orientation of the plug, this used to be a problem back in the day because all plugs were the same size, and you could just turn it around and you'd end up electrifying the outside of your metal drill case instead of electrifying the internal part of the motor. It would still run, it's just if you pulled the trigger, you'd get a shock, okay? And part of the reason you get that shock is because you are completing a circuit with the ground. Turns out you are a faster route to the ground for that current than the wall is, okay? And so for shorts in devices or plugging things in backwards, this was a problem. They started inventing the polarized plugs. You know the ones that are annoying. You can only put them in one way. And then you get those little brown extension cords that nobody's bothered to update. And you're trying to shove the polarized plug into the little brown extension. Yeah, don't do that, okay? Get a decent extension cord. The ground wire in these systems, okay, that third wire, even if you've somehow managed to get like a short in the device or a reverse polarity in the device or whatever, that ground becomes the faster return path. It has less resistance than your body does, and it keeps the user from being shocked. What the GCFI does is it trips when it senses that there's too much current running through the ground, okay, in the circuit of your house. And that way it knows, we've connected current, we've connected hot to ground, this is bad. Because you connect hot to ground, the resistance is really low, current's going to get high fast enough that that circuit breaker may not be able to trip before it auto-ignites the insulation in the wall or something like that, okay? So that's why a GCFI will cut it even faster than a regular circuit breaker would. And in more modern homes, like homes made in the last 5 years, I think every outlet is basically, like the GCFIs are in the circuit breakers themselves, in the panel in the wall. They're not a separate outlet that controls it. So look for those things in your house and look for safety. What the heck is this? That's a neuron. What? Why is a neuron on the screen? Quite possibly one of the most complicated and beautiful arrangements of electrical circuits, okay, that have ever graced the surface of the earth. So a neuron in your brain, right? Okay, it's got all of those dendrites that go off and connect to other neurons that then make up your brain, your memories, your sensations, your emotions, all that kind of stuff. Then there's the axon, the thing, like the long body of it that goes off to other dendrites. Some of these axons, the connection from the neuron to where it terminates, aren't they up to a meter long or something? There's some that start in your brain, go all the way down your spinal cord, and then terminate down your legs or something. They're basically like a single structure, right? So when you feel something, right? What happened? That sensation of touch. How did it get to your brain? Through the neuron. But how did the neuron do it? It's an electrical circuit, isn't it? So there's a nerve ending somewhere that is getting excited, right? Woo-hoo-hoo! Pressure, something, heat, temperature, whatever, right? And it gets excited and begins a chemical process that involves ions, potassium ions and some other things. Those are potential differences across the cells that make up this structure. And there's this cascade of electric potential signals that get sent along the axon all the way up to the cell's nucleus, right? And then that communicates and fires off to the other ones. And over time, you've learned to associate the patterns of those electrical signals. You are a walking circuit. I mean, chemists will think of you as just a bag of salt water, right? And of course, you're much more than just a bag of salt water, okay? But maintaining these electrical connections becomes important. Multiple sclerosis, did I get the right disease? Is what happens when the sheath, the myelin sheath around a axon and a nerve starts to degrade. And you start getting short circuits between the nerve pathway going back to the brain and the rest of the body. And people with multiple sclerosis end up not being able to control their arms and their legs, and they either get weak or they can't manipulate things, and as that sheath starts to degrade. The sheath is like an insulator around a wire kind of thing. I thought I would bring that up, right? Because I know a lot of you sitting in here, you're not going to be electrical engineers, right? And you slog through all of this stuff going, oh, I can't believe I have to. I was the same way. I was like, I don't ever want to do circuits again in my life. I'm an optical physicist. Let me play with light, right? Electrical circuits are everywhere. As I told you, I managed to plug myself into one in the lab, right? But there were so many times I had to sit there and solder circuits together to get my work done, right? Whether you're in biology, mechanical engineering, I'd say the only people that are safe in here would be English majors and civil engineers, okay? Because civil engineers, they can go build stuff. Thank you for building the structures that define our lives, right? But you really aren't going to have to worry about circuits too much in civil engineering. So some of you are going like, right? But for the rest of us, circuits, they're there. They're everywhere. They really are. And knowing what you know about them is important. Thought I'd throw this one at you. We don't have to do this as a quiz, okay? But I've been known to pull similar stunts on exams to this, okay? Because I think it's a funny, clever way to find out whether or not you understand Kirchhoff's rules and the conservation laws that are behind them. So, the question is, how would we apply Kirchhoff's rules to a water slide fun park? Right? What I want you to do, okay, is turn to each other and try to figure out what would two slides connected in series be? What would slides connected in parallel, right? Go through A, B, right? See how far you get, but try to figure out what this would look like if you were at a water slide park. Go. All right. Two slides in series. What would that describe that for me? What would that look like? One after another. Meaning that if you ride like the first one, where does the outlet of the first one take you? To the input of the next one, right? So that would be two slides in series. So what do two slides in parallel look like?
One line to multiple slides.
So you climb up the stairs, right? And when you get to the top of the stairs, there'd be choices, right, as to which slide to go down. They might do different things on the way, but they're in parallel because the beginning and the ends end up at the same place, right? You start at the same platform, you end at the same pool. Okay? Sketch a junction of one stairway and two slides. So stairway. Slide 1. Slide 2. Or spaghetti. I don't know what that is. Okay. Right? So there's my sketch. So stairway goes up. Two slides come down. Okay. State Kirchhoff's junction rule for water slide fun parks. What's Kirchhoff's junction rule for currents? Current in equals current out, right? So how would we restate this idea for a water slide fun park?
Slides come back together. Once you climb those stairs, you gotta come back down.
Okay, so it's conservation of people here, right? Because the underlying thing about the junction rules is conservation of charge. Whatever charge goes in, that's the amount of charge that has to come out, right? So if 10 people go up the stairs, you better have how many people coming out of the slides at the bottom? 10. If 10 people go up and only 8 come down. Or if 10 people go up and 15 come down. It's problems. So it would be a statement of conservation of people, wouldn't it? That idea that 10 people go up and 8 come down one slide, 2 better be coming down the other. Okay, one person is a physicist, of course, and she's brought an altimeter. Oh, Kirchhoff's loop rule for altitude. So the loop rule in circuits is all about what? voltage, isn't it? It's about potentials as you go around the circuit. So instead of like electric potential, this altimeter is measuring something more like gravitational potential energy kind of idea, right? So what would be true for the physicist if she starts at the bottom of the stairs and rides and comes back to the exact same point she started at? What would have to be true about her altimeter? If it read 0 to begin with, it needs to read 0 at the end, doesn't it? So that if she goes up 100 feet and then rides 3 water slides, what was the total drop across all 3 of those water slides? 100 feet, right? For a closed loop of the water park, the change in altitude needs to be equal to 0. Meaning that she gets back to the same altitude that she started at. Those are the kinds of things I need you to be able to do, right? These concepts and ideas behind what's going on can be applied in a lot of different ways. And this is one way that I can find out if you understand that Kirchhoff's, not just how to apply them, but do you understand that Kirchhoff's junction rule is about conservation of charge, conservation of things in and out. And Kirchhoff's loop rule is conservation of energy, right? What goes up must come down, that kind of thing. So, all right. RC circuit. Let's quickly do this and then let's do some homework. An RC circuit means that the circuit has a resistor and a capacitor in it. It does not mean remote control. That's different. Okay? So I've got a battery here. And then I've got a resistor and I've got a capacitor. So here's, I'm not going to actually solve this. I'm just going to show you what's going to go wrong in a hurry, okay, with a situation like this. Where's my, right here, okay. And let's say that we take this circuit, we hook up this battery, right? What's going to happen? Time 0. Capacitor's not charged. What's going to happen? Is current going to begin to flow? Is charge going to leave? Is the battery going to push charge onto the capacitor plates? Yes. It's going to have to do it through the resistor, isn't it? Which means that instead of sort of like instantaneously piling onto there, the capacitor will charge over time. The resistor, what do resistors do? They slow down thing, right? Okay. So it's slowing down like the rate at which this capacitor can charge up. But eventually, would this capacitor charge up? Yeah. I mean, there's nothing to stop it going through the resistor and getting to the capacitor plates. So eventually, right, we would get to a situation where the battery, at whatever voltage it's at, okay, and the capacitor will be at that opposite voltage or same, right? It's like positive and negative here, and then we're piling positive and negative things right there. And as soon as the capacitor gets to its charged state, what does the current in the circuit become? 0. The battery's trying to push with 5 volts, whatever, right? Okay, upwards. The capacitor's now balanced with the battery and it's pushing the other way backwards. And so the current in the circuit's going to go to 0. So we have a situation here where our current is changing over time. Up to this point, we haven't done that. We've turned things on, we've turned things off. We just assumed an instantaneous, right? The current's there, the current's not there. This current is really big to begin with, but over time, as that capacitor gets charged more and more, it's going to slow down. So how do we work our way through this? Okay. So let's do the, let's do a loop rule. Can you simplify this circuit any more than it's already? No. Okay, so we can't simplify, we can't combine capacitors, resistors, So I'm left with Kirchhoff. Like Kirchhoff's rules will always work, no matter what. The rules for series and parallel and same in voltage, those are outgrowths of Kirchhoff's rules. You can actually do those circuit loops that you can do Kirchhoff's rules with all those resistor only problems and stuff. It's just it tends to be too formal a process. So let's just do a loop around this circuit, starting right here. Okay. First thing we pass through is the battery, right? So I'll just call that the EMF coming out of the battery. And then I'm going to assume the current is flowing this way. So current and loop are in the same direction. So positive and or negative for that resistor. It's negative. It's a voltage drop. It's going to be the current times the resistance. And then what do we do for the capacitor? So what we're doing here is we're trying to, we're summing up all of the changes in potential, right? And setting it equal to 0. So this eventually has to get to 0. But how do I write down the voltage of a capacitor? Do you remember? What's the relationship between voltage and capacitance? Yeah, wasn't it Q equals CV? So that means that the voltage is going to be the charge divided by the capacitance? Yeah? Okay. That would be total charge over capacitance. I'm going to write down little q just to be different, to indicate that there could be differing amounts of charge on this capacitor depending on time. But there I have Kirchhoff's loop rule for this simple circuit. I've got a constant EMF. I've got a drop of voltage across the resistor, which changes with current. And then I've got a voltage across the capacitor that changes with charge. We want to solve this for the current or the charge. Doesn't matter. I want to solve it for those two things. Does anybody see the problem? What? Yeah, they're changing, so. I mean, X and Y change. One of these things is a derivative of the other. What's current? It's a change in charge over a change in time. We can write it as a delta Q over a delta T if we don't want to do instantaneous. But it is a change in charge over time. It's charge per time flowing through a conductor, right? So that means that my equation over here is EMF minus dq dt times the resistance plus Q over C equals 0. And what kind of equation is this? Shouldn't have boxed it. I'm not done. What kind of equation is this? That's a differential equation. Is it a first order difference? I think it's first order differential equation. Okay? Which means we need differential equation tools to solve it. How many of you are in DiffyQs or taken DiffyQs and know what a differential equation is? Is it like 2, 3? Okay, all right. So for the 2 or 3 people that haven't taken it, don't panic. You're not going to have to do anything. But let me tell you the secret of differential equations. Is this math 17 also? Okay. Math 17 day. The way that you solve every differential equation is by guessing. I'm not kidding. Every thing that they teach you in Math 17 about solving differential equations is just fancy words for guessing. You guess the answer, you try it. When it doesn't work, there's typically some clue as to how you need to change your guess to make it work, and then you try that again until it works. I've done math my entire life by guessing. When I hit differential equations, I had to take a whole semester of it. When I hit differential equations, I had finally come home mathematically. Algebra, I guess. Geometry, total guess. Trig, guess. And I didn't do good. Differential equations, I rocked differential equations. Right? I could guess with the best of them. I had honed it for 21 years. 21 years of guessing how to do math. And I finally was in a math where I could guess. You'll see. There'll be all these methods of differential integral, blah, blah, blah. It's all guessing. It's all just honed guessing, I guess is what it is. Anyway, you guess the answer, okay? And this is the answer that falls out, okay? So basically there's just a big a miracle occurs step here where you guess, okay? And when you guess, it turns out that the current as a function of time is the EMF of the battery divided by the resistance. Now, okay, so this starts off really good, doesn't it? Because what is a voltage divided by a resistance? Like Ohm's law? It's current, right? Like, this is good. It's good first step. This is where it all goes wrong. E to the minus t divided by RC. Who ordered that? Can you see maybe a little bit how that answer had to have an exponential function in it? The differential equation is telling us that we need a function of Q. By the way, the charge version is the total charge 1 minus e to the minus t over RC. Okay? The differential equation says Q as a function of t, its derivative and its actual function have to be very close to each other. To be able to add these things together, whatever so what's the derivative of, I don't know, x cubed? It's 3x squared, isn't it? Does x squared look anything like x cubed? No. Right? Those two functions they don't look like each other, right? What's the derivative of x squared? It's 2x. Does the equation of a line, x, y equals x, look like the equation of a parabola? No. So those can't be solutions. Functionally, the solution for Q can't be a power of something. It just doesn't work. Okay, so basically what I need is something that repeats itself, right? If I take its derivative, I get the same thing out. Does sine or cosine work? No. Because the derivative of a sine is a cosine or whatever with a negative sign in it, right? They kind of flip-flop, right? And the two functions are out of phase with each other. So that doesn't really work. So can anybody guess the function where when you take its derivative, you get the same function back out again? This is why I love differential equations. If it's a first order, the answer is E. If it's second order, in other words, you have to take two derivatives and get the same function out, then what are your choices? Sine, cosine, or E, right? Because what happens if you take sine twice? You get back to sine, don't you? What happens if you take cosine twice? You get back negative signs. It's in the details, okay? But basically, I've just solved every first and second order differential equation. Done. I've saved you an entire semester's worth of, no, I haven't. Okay? It gets messier than that. Okay? Especially when you get to orders of differential equations that are bigger than 2. Okay? But this is the solution. These are the equations that govern the charging of an RC circuit. This is what the current and charge per time is for a circuit that is charging. We can do exactly the same result, we can do exactly the same thing for a discharging circuit. So this would be charging. Okay? And then for discharging, I can spell, discharging. The circuit in a discharge removes the battery. So you have a resistor and you have a capacitor. The capacitor starts off charged and begins to discharge through the resistor. And so your equation is basically Q over C minus IR equals 0. There's no input of constant voltage in this function. And what you end up with there is the current as a function of time is equal to negative Q over RC e to the negative t divided by RC, and the charge as a function of time is equal to Q e to the minus t over RC. Do you see how the RC, resistance times capacitance, always seems to be coming together? R times C is often called the time constant of the circuit. The more resistance and capacitance you have, right, the bigger those denominators become, which means more time is required to get this thing to charge. What does an e to the whatever look like? What does that function, e to the minus t over RC, look like? So as we charge, right, it kind of goes up. Doesn't it do something like that? Right? Where we're getting to like some, no, it's the other way. It's negative. It starts off big and then gets small. Jeez. Okay? So your current starts up here, and eventually, as time goes by, right, it gets smaller and smaller and smaller. Okay? Current starts big, gets small, and then for the discharging one, that's where you're, that's the same. We'll just leave it at that. But you got the equation. And I think I gave you one homework problem, which is like find it when it's halfway to the current or something. Put in half the current. Solve for t. How do you get t out of these equations? Natural log of both sides, right? Just brushing off some of your little natural logs. That's a preview for the kinds of things we're going to work on when we finally get to AC circuits. So what the rest of this class semester looks like, okay, after this exam, is we jump back into field theory, but now it's magnetic fields. So all that field stuff we did with electric fields, coming back, but with magnets, north and south poles and that kind of stuff, okay? Once we've tackled magnetic fields, that unit, which is a big unit, we then move into applications of magnetic fields and electric field and everything together, and that becomes the alternating current circuit. AC doesn't work unless we understand what magnetic fields are doing. Okay? So we finish up the semester in AC circuits. AC circuits are time-dependent circuits. So while this is a DC situation, we put a battery, which gives direct current. We're starting to get hints of the time component in some of these circuits. As we switch into AC, it's all time, everywhere, all the time. And we'll deal with that when we get there. Let's take a look at your homework, though, and see if we can't make sure that you've got some good direction for what's going on for that. So let's see. I've got to switch a little bit. Be able to pull up the homework. Let's get... Ooh, somebody won. going on? Let's see. This is chapter 27. Homework is due on Monday, right? This is not what you see. You see this. So conceptual questions. Oh, good. Practice on whether things are in parallel or whatever. Okay. Yeah, okay. So these are, let's make this a little bit bigger. Okay. What is this question about? Yeah, what's the concept behind this question? What do you need to know? This is resistance in series or parallel, right? Okay. The total is 3.3, and an unknown and a 12.26 get added together. What's the only way the resistance can go down? It's a parallel connection, right? So that's really what this one is about. Okay. 4 resistors all the same. They're connected in parallel. Find the current. What does 4 resistors in parallel look like? Like schematically. And then the battery can go down here or up here. It doesn't matter. It could go off to the sides. Okay. Like there. Okay. So there's my 4 resistors in parallel. They're all the same. Math is a little bit easier, but again, this one's is asking you to work through series and parallel. Ah! Oh, wait. I don't even know what they're asking me. All the R2s, they're all the same right there. How are they connected? Parallel. They're being a little bit, they're trying to trick you. The part of the circuit that's down there in the lower left that looks like, thank you, they're clapping for me. This is great. Okay, so what class is that? I appreciate the clapping. Sorry, had to go poke fun at the engineers. Okay, so these wires right here, is there a different way to draw that? There's like a wire that goes up like that, right? And there's like a wire that goes. All of this right here is all the same junction. There's no magic is going on here. Just these are all just connected to each other, right? So you can think it's all. So these are all in parallel with each other, right? You don't need to break just these two, right? Which then you find out is in parallel with this. The math ends up being the same, okay? So watch out for stuff like that. Oh, instantly know from the picture. What is this? This has to be Kirchhoff. How do you know it's Kirchhoff's? It's 2 batteries, right? This is a Kirchhoff's law problem. And it looks like they gave me the directions of the currents. They usually do that because they've hard-coded the positive and negative answers in. So do we get to pick? Yeah, we get to pick the direction of the loops there. So that's a Kirchhoff's law problem. You've got to be kidding me. Why would anybody do this? Actually, this is called a Wheatstone bridge, I think. It's a rudimentary voltmeter, believe it or not, when you hook up stuff like this. So it might not be exactly a Wheatstone. I'd have to go look up Wheatstone bridges. But what the heck is going on here? Oh my gosh. How do you... What's in parallel? What's in series? This pen is going. This is a bad pen. What? I mean, even I can't really look at this and go, oh, this series in parallel. So if you can't do series in parallel, what's a fallback? Kirchhoff. How many loops are there?
Wait.
One. Does everybody see that loop? Okay. Two. Right? Three. Four. Five. And six.
No, it's okay. I see it now. You're good. Is there not a 7th one? I'm at a 6.
Okay, I mean, I guess you could do that loop.
But the resistance on the
Okay. But in this particular case, because of the way they've done it, because the resistors here and here are the same, and here are the same, my black and blue lines on this diagram are actually the same loop. Even though they kind of went different directions, the fact that I've got a symmetry or a mirroring of my resistances, you end up getting the same equation, the same relationships between things, okay? I'm calling this out because this one is, I don't know if it's impossible, but I can't see what's parallel and what's not, and what's in series and all that kind of stuff. But I can identify pathways or loops through, and if I can get enough of these that I can write out Kirchhoff's laws, then this is solvable. Okay? And I believe this one turns out to just be two equations, two unknowns, but don't quote me on that one.
How do you draw the current from? How do you know which direction they're going in?
You don't. You just guess. I would go current there, current there, current there. Well, now I know that these two currents have to be the same. How do I know?
Because they're the same.
They're the same resistance and they're the only thing on that side. So, but you could actually use different currents down here and then mathematically it would all work out. You'd end up with 5 equations with 5 unknowns, but you very quickly see that those have to be the same. So, yeah, you just guess. And it could be backwards, right? The sign will just tell you that you guessed wrong. But yeah, yes?
So the loop doesn't have to start at the battery?
No.
Okay. There's still a current around the outside.
Doesn't have to start at the battery. There are 2 junctions that I would call important. That one and that one, but they end up being the same equation again. Again, because of the symmetry of the problem. Point is, not every Kirchhoff's law has 2 or more batteries in it. You can apply it in situations like this. If you think this one's bad, I mean, this one's not so bad. Because R2, R3, and R4 are all what? They're all in parallel. You can actually redraw this one. That branch over there can be drawn exactly like this. Have I maintained exactly the same connections? That one's not so bad. Kirchhoff's. It's got 3 batteries in it. I told you there's one. What is this? RC. Okay, charging or discharging? Charging. I gave you the equations. They're also in the book. Have fun. Okay, well. It looks like it's 4 problems in one or something. Okay. A lot of batteries, huh? There is a hard way to solve this one. And there is an easy way to solve this one. Those of you that haven't looked it up yet, okay, because I'm sure the internet knows the answer, right? Let me just tell you, here's your hint. The solution to this one will amaze you. Emphasis on the word maze. There is a path through this circuit that is easier than all of the rest. See if you can't figure it out. And be grateful I didn't give you the resistor cube. You guys probably don't know what that is. Take a cube, and on all the edges, put a resistor. Find the equivalent resistance. I did not give you that problem. Have a good rest of the day. I hope to see you on Friday.